Okay, so as we move into chapter 9, we start to use our knowledge from chapter 8 in terms of some application questions. And in some cases, very early in the chapter, we start to look at combining some of the different concepts. So for example, if we have a look at analysing reducing balance loans with recurrence relations, this is where sometimes we have scenarios that involve both linear and geometric growth. So it's a combination of both. So we may get a situation where we have a recurrence relation of the form VO equals 0, which is our starting value that we're familiar with, and then Vn plus 1 is actually made up by looking at and calculating R, capital R, multiplying that by Vn, which was our previous term that's known to us, and adding or subtracting D, which is the linear component. So R times Vn is the geometric part, plus or minus the linear component in this case, which is D. So if we look at the example there, we have VO equals 3, which is our starting point, and our recurrence relation tells us that in this case, capital R is equal to 4, and we have to multiply that by Vn minus 1. So here we're asked to write down the sequence that this particular recurrence relation generates. So we know we're starting at 3, we're multiplying that answer by 4, and we're taking 1 to get 11. Our next step is to take that 11, which becomes our new Vn, again multiply that by 4 and take away 1 to get 43. And when you continue that, you have a sequence of 3, 11, 43, 171, 683, etc. Okay, so example 2 here now looks at modelling population change using a recurrence relation. And this example here is a really good one and one that is often referred to. So it's a scenario where we have a number of trout in a farm, a fish farm pond, and as part of this, we know that the fish are growing and they're multiplying, but we're also taking some fish out of that pond at particular times. To eat, yes. So the recurrence relation here that's given in this question or this scenario, we're told that TO equals 10,000 as our starting point. So we start with 10,000 fish in the pond, and then the sequence here, the recurrence relation here is Tn plus 1 is equal to 1.1 times T of n minus 3,000. If we break that down, 1.1 actually represents capital R, and because we know capital R is 1 plus little r over 100, we could work out there that little r is actually 10%. So this is telling us that the population is increasing by 10% each month. But that minus 3,000 tells us that we're taking out 3,000 fish each time. So the question there asks us to determine the number of trout that are in the pond after 2 months. So if we use that recurrence relation, we've started at 10,000, then we've said that answer is multiplied by 1.1, which is capital R, and then we're taking out 3,000. So after 1 month, we have 8,000 trout in the pond. If we repeat that using that 8,000 as our next figure, after 2 months there are 5,800 trout in that pond. And part B there, after how many months will there be no trout left in the pond? If you keep that iteration going and that sequence, you'll find that after 5 months there will be no trout left, because if you look at that, after 4 months, there are still 718 left in the pond. But then in the 5th month, we're going into negative numbers, which obviously is impossible. And in this case, we say that there are no trout left after 5 months.
Easy.
Okay, so that same principle can be applied to reducing balance loans, because when we borrow money from a bank, we don't wait to the end of the period before we start paying it back. So yes, that amount that we initially borrowed is increasing because it's being charged interest, and that's where R comes into play, but then we also are contributing payments towards paying that off. So generally a loan is made up of a couple of things. The first thing, our starting point. Secondly, the rate of interest. And thirdly, the repayments. In the scenario of a personal loan or a mortgage, that's how that would work. And we look at various examples as follows. So we're still using exactly the same principles there. In this case, VN represents the balance of the loan. So what we start with is our principal, VO, but VN, we can look at any point in time and we can actually work out how much do we still owe back to the bank. So that that includes the interest and D, the payments that we're making back. So a recurrence relation looks like that when we're talking about a reducing balance loan.
So if you remember this formula, you're not going to have a problem.
Okay, so the next example highlights how that would work. Someone's borrowed $1,000. The rate there is 15% per annum. Let's highlight the fact that it's saying compounding monthly. That means we've got to do something to N. We've got to use N. So we've got to divide that little r by N to factor that in. And then we're making payments back of $257.85, and they're monthly, and when it says there she wants to repay it in 4 monthly payments of that. So the question there asks us to construct a recurrence relation to model that in the form VO equals the principal and then using that general formula. So we need to calculate what is VO. Obviously in this case it's $1,000 because that's what she's borrowed. We need to work out capital R. So in that case, it's 1 plus R over N divided by 100.
So I'm just writing down the variables, Miss, here because so that we know the initial. So the initial VO is 1,000. Yep. And then I've got capital R equals 1 plus little r on 100.
No, over N.
Over N, what am I doing? Okay.
Yep, over here. Just.
Yep, I do that,
yep.
Yeah.
You do it at the end.
So I do it at the end. So what happens is it says compounding monthly. So our months are going to be compounding by 12. So you just do the little 12 like that. And then you get into R as being 15 divided by 12 because it's 15% per annum, which will give us 1.25% per month or 0.0125. So
That's
our
right.
R is now 1.0125. Like
and
that.
D is minus 257.85 because you're paying that back to the bank.
So they're charging us interest,
yep.
But then we're paying a little bit off.
Yep.
And we do that for 4 months. So the model will look like this. Vn plus 1 equals 1.0, that's a negative, 1.0125 times Vn minus 257.85.
Okay,
So,
just to highlight that the full answer to this question must include VO equals 1,000.
that one there.
Yep.
And
then the actual rule. Okay, because if you don't present both parts, that's not complete.
So now this part, example 4 is just answering some questions based on that relation that we created. So we'll go through this one as well. So the first one just says, use your calculator to determine recursively the balance of the loan after Alyssa has made each of the four payments. So they should be okay with this because all we're doing is 1,000 enter, then times, that'll give them ANS on their graphics calculator. So we do 1,000 enter, and from there, guys, you get ANS, and then you do times 1.0125, and then minus 257.85, and you'll see this on the next screen. When you keep pressing enter, 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 there you go, 1, 2, so that's initial 0, there, 1, 2, 3, 4 months, like that. And you'll get, the actual question, Miss, was what?
The question...
Use the calculator to determine the balance of loan after this has made each of the 4 payments. There they are there. So after the 4 payments, what have we got? 254.7, so 4 payments, that's 1, 2, 3, 4. What's that one there?
Okay.
4 cents?
4 cents. And that has to be, because part A there, use your calculator to determine recursively the balance after she's made each of the 4. So that's what she owes there after 4 is simply the 4 cents. Okay, because that's what's left over. Part B asks what's the balance of the loan, so the amount she still owes after she had made only 2 payments. Okay, and we could
so we've got to look at
go back to what we had calculated there. So $506.23. That was already in our calculation. But Part C is asking, is the loan fully paid out after 4 payments? Mm-hmm. And we know that it's not, because 4 cents is left over. And that 4 cents...
You've got to pay it back.
You have to pay it back, otherwise it keeps the account open. So your final payment, the 4th payment, is a little bit more. It's actually 4 cents more than your 1st, 2nd and 3rd payment.
So then it'll be like $257.89, won't it?
That's right.
You add the 4 cents to that last.
Exactly, and that's what's there.
That's it. Easy. It's not hard. All right. Amortization tables. Here we go. Loans that are repaid by making regular payments until the balance of the loan is 0 are called amortizing loans. That's what I'm doing at the moment, miss, and what we do normally when we're trying to pay off a loan. In an amortizing loan, part of each payment goes towards paying the interest owed on the unpaid balance of the loan, with the remainder used to reduce the principal of the loan, the amount borrowed. So, for example, let's consider the loan before. So $1,000 was charged at 1.25% per month, and the loan was to be repaid with 4 monthly payments of $257.85. So the first step in the amortization process is shown here. So the principal is $1,000. We have to add interest of 1.25%, which is $12.50. So I actually owe the bank at the moment $1,012.50 because we have to add the interest, and I haven't made a payment yet. So what happens is I owe them plus interest. I've paid them $257.85. So if you minus that from $257.85, that's your new balance, everyone. So when they're saying here reduce principal, $245.35, that's all I've paid off, not the $257, because included in that is the interest, and that's why that is there. So at the end of the first month, when the first payment is due, we know we owe them $12.50 on top. So what happens is you're paying them $257.85 minus the $12.50. That's where you get this amount from. That's all you've paid off, even though you paid a bit extra. So the $245.35 is then used to reduce the balance of the loan to give you a new balance. That's what you actually paid, because we paid $12.50 in interest minus that, so we still owe the bank this much. Then for the next month, it's on that amount, isn't it?
Yes.
So that's what happens. So the next month, it's on this amount. Again, do you notice that what's happening to the interest? It's less for the second month because I'm not paying off $1,000 anymore. I'm paying off the $754.
So as your balance is reducing, the interest is also reducing.
And so is the amount of principal. The amount of principal that you're paying off is also the principal increases here.
Increases, yes.
Yeah, so you see that there, the 248 and was 245 before. So you're actually increasing more, but you're reducing your loan anyway at the same time. And then that's your new balance for the third month, and it just keeps going on and on until you see something like this. So this is your amortization table. So if you start off at 0. Look at that. All the way there, you owe $1,000. What stays the same is your repayments, except for the last one. Remember that? There was 4 cents left over there. The interest starts to decrease, and that's your total interest. And then your principal reduction increases higher because you're reducing your principal amount by each month, because you're paying off all this money, and that's why you get $10,000 here. And then that's the balance at the end of each month till you get to 0. Okay.
Now, that interest that's been paid, that's been calculated based on the previous balance. So the $12.50, that's the percentage, the rate,
Yeah.
the interest rate. That's
1.25% on that 10,000.
1.25% of the 1,000. The next one, that $9.43, will be calculated using $7.54 and 65 cents.
Same percentage.
Same percentage. Okay, so when we look at analysing reducing balance loans with recursion relations, we look at the properties of the loan. So what are we starting with? What's our interest rate? At each step of the loan, if we want to work out how much interest has been paid, we look at the interest rate per payment period, and we multiply it by what hasn't been paid off. For example, when the payment 1 is made, the interest, as I was saying earlier, was 1.25% of 1,000. Okay, so that's $12.50. The principal reduction there is the payment made less that amount. So $257.58, which 85 cents, which was D, our repayment. Take away that interest amount, which is $12.50 in the first payment. And if we look at what that looks like, if you go to part 3 there, the balance of the loan is what you owe, take away the reduction in the balance. For example, in that case, we had 1,000 that we started with. We've taken away $245.35, not our repayment amount of $257.85.
Correct, because we owe them $12.50 for servicing that loan for us.
Exactly. So then in question 4 there, the cost of repaying the loan is the sum of all the payments. So all of those individual payments plus that final one, which was a little bit extra. So if we look at that, if we add all of those up, that's $1,031.44. We know that we borrowed 1,000, which means the total interest is that amount take away what our principal was. So we've paid $31.44 in interest over that period of 4 months. Now, finally, if you have a look at the graphs there, for that particular loan, it's showing the amount of interest from each of the payments has decreased, and that's represented in the blue dots down the bottom of that graph, and the red dots are looking at how much principal you're paying off. And if you have a look at that, that's been increasing as time has progressed. Okay, so if we have a look at example 5, the reading and interpreting of the table here, we've started off with $10,000. It's been borrowed at a rate of 8% per annum, but that loan is to be repaid, making quarterly repayments of $2,626.23. So automatically we know that 8 needs to be divided by 4 to get 2%, and we have that's our interest rate for this particular case when we've got 1.02. So the box that we need to fill out there is, well, what is 2% of that 10,000? So we multiply that as 2 over 100 times 10,000 to get $200 in that particular first square there. When we take that 200 away from the payment of $2,626.20, we have a principal reduction of $2,426.20, and therefore our balance is now $7,573.80. Now we're going to use that. If we find 2% of that, you will work out that the interest, 2% of that balance there, works out to be $151.48. So that's where they've picked that up. But we need to calculate, well, what's the principal reduction? So we have to take that away from our payment, And we end up with a principal reduction there of $2,474.72.
Perfect.
So now we have
how are they getting now 5,099 on the next line?
Okay, so that's our balance to say, well, by paying off our payment, how much have we actually reduced this by? We've reduced it by our previous amount there in the principal reduction, and we've ended up with $5,099.
So that 7,573.80 in the previous minus
2,600. Yep. Oh, sorry.
Or the principal reduction, yep. 2,474.72.
Right.
That gives me 5,099.80. So in order to get the next box without even thinking about it, it would be 5099.08 minus 2524.22, which will give me
$2,574, I believe, and
86 cents. So correct. That's that one, and then we've done that. What have we got to do for the other empty box down here?
Okay,
right there.
So that's the total interest that's paid. So we have to add all of those together.
And when we add them up.
And we add them up to the principal reduction.
So 151.48 plus 200 plus 101.98 plus 51.50 will give me a total of?
Well, our total interest is $500.96.
Beautiful.
And we add that to 10,000. Now, could I just highlight something? The box that we were filling out there, because we knew that column had to add up to 10,000, we could have actually just subtracted the other three principal reductions.
So we didn't have to do all of that.
So that was a quicker way, I guess, to do that. So that's just a handy hint going forward.
Easy.
And that whole area there now encompasses 9A and 9B.